So, I hope you have enjoyed the first week's lectures. If there are any problems, you can always write back to the forums. My teaching assistants would definitely help you out. It is the second week now, and we are going to end our discussion on limit and continuity. Today we are going to talk about a very important limit. Limit sin x by x as x tends to 0 is 1. There is another important limit which we are not going to talk much about, but we will show that it can be used to compute the derivative of logarithm of x when we do it from the first principle, and that limit is it looks very strange because you see at 0 neither this function is defined. So, when we were talking about limit f x tends to a is equal to L, we always had a deleted neighborhood because we never considered a in the neighborhood surrounding a, because at all points in the neighborhood other than a we expected the function value to be computed, that part has to be in the domain of a, but a need not be in the domain of the function f. Here you see, or whatever x that you take in both sides of 0, sin x by x is a perfectly valid function, it has a numerical value, but at 0 it is meaningless because it will become 0 by 0. Then but it still has a finite limit. So, this is f x, this is your a which is not in the domain of this function, your 0 is a here, a is 0 here and L is 1 here. We are going to give you a very small geometric proof of this fact. There is also another easy proof of this fact which you will learn when we will talk about L'Hospital's rule of finding limits when we are going to study derivatives in the next classes. See, it is important to understand that whenever in trigonometry we are talking about sin x, cos x, tan x, whatever, this x is measured in radians. Okay, radian, what do you mean by radian? It is radian is the angle. So, here is your circle. So, say circle of radius 1 centimeter. So, if you sweep an arc of length 1 centimeter, then the radian that is swept, then the angle that is swept, this angle theta, if this is also 1, then this angle theta is called 1 radian, and 180 degree is pi radians, and that is the interesting thing. So, 180 degree is pi radians. So, 1 radian is pi by 180 degrees. Okay. So, x radian is 180 by pi into x degrees. So, if you want to compute the radian out of the degrees, for example, when you put x equal to pi, where pi radian, that becomes 180 degrees. When you are putting x equal to 1 radian, you are putting 180 by pi degrees. This is very interesting that you can play a lot with this thing pi. So, when you want to compute x here, but when we are doing actual computations, we are essentially concentrate with degrees. When you take a compass at school, we do not talk about radians, we talk about degrees. So, when we are talking about degree of the angle, then if I give a degree, I should be able to calculate the radian, because in mathematics when you are calculating, on trigonometry when you are calculating these sort of sine and cos functions, then you are essentially talking about radians. Now, the question is, can I make a guess? It does not seem that I will right away write down a proof. I can write down this result if I know the L'Hospital's rule. If I do not know the L'Hospital's rule, writing this result may not be so easy. It needs a slight bit of geometric intuition. So, when we do not have our geometric intuition right away, when we do not have any analytical tool right away to compute this, we have to depend on experimentation. Experimentation via computation is now one of the central themes of mathematics. Mathematics was largely an experimental tool, experimental subject long back in antiquity. People did computations and then tried to understand whether certain things are true. But in many cases computations cannot be done for infinite things, computation cannot be only done for finite number of things. But the importance of rigor in mathematics is that if a thing can be true for a finite number of numbers, but a thing may be just not true after that. So that is why you need to talk about proof, that is why you need to talk about rigor. For example, many of you have heard about the Fermat's last theorem, which says that if you have an equation of the form x to the power n plus y to the power n is equal to z to the power n, if n is bigger, strictly bigger than 2, that is 3 and above, then you do not have any integral solutions to it. Of course, there was a huge trial for this, proving this problem. People proved that okay, if n is 3, 4, 5 or n is up to 10,000 I can prove this, but that does not make it a result, because okay, up to 10,000 I know that this is not true, but beyond 2,000 there could be n for which it is true. To prove it finally, what Andrew Wills did need a very sophisticated level of now mathematics. So, but experimentation is very important, as we are coming back to experiment nowadays, and there is a separate branch of mathematics called experimental mathematics, because experiment is always giving you an insight. It tells you that possibly this is the way to look for the answer. Here what I do, because x is going towards 0, I tend to decrease the degree. Of course, if x is if y is 0 degree, then we have 0 radian. So when I am decreasing the degree, I am decreasing the radian also. So for 10 degree you have this, sin x is this, sin x by x is this. For 5 degree, this is your radian 0.873, then you compute sin x, then you compute sin x by x. Again when you come to 2 degree, because we have approximated the calculation, it looks like this. So this little calculation is due to Courant and Robbins, but it is found in other places, from a lovely book which anybody interested in mathematics should read, and it is a serious book called What is Mathematics. Of course you can say, oh, 2 degree is far away from 0, 1 degree is very far away from 0, so how we are getting 1. Now if I go down further, I would leave it to you to compute it down further, because now you know how to compute it, you know what to do, you just put in a degree, get the x, compute sin x. Computing sin x nowadays, okay, if you can do it with a calculator, just do it with a calculator, and then see what you get sin x, what is the value of sin x by x. So I believe you will continue to get 1. So basically then you can have some confidence to say that that limit of sin x by x is actually equal to 1. But that needs a proof. This is all guesswork. Of course this gives you a lot of confidence because you have computation in front of you. So computation is there to gain insight, and now let us talk about a proof. So what we do is that we take the circle where O is the center, and it is a unit circle. The radius OB is equal to OC is equal to 1 cm. It does not matter if you do not like. If you are uncomfortable not writing a unit, write 1 centimeter. So it is called a unit circle whose radius is 1 unit, 1 something, could be meter, centimeter, let us just take 1 centimeter. Now what you do, let x taking B as the base, OB as the base, you sweep out a angle of x radians, of course which is non-zero, and let it cut the, when you sweep it off, it stops at the point C. So BOC, this angle is of x radian, where x is not equal to 0. Now what you do, from C drop a perpendicular on OB where it touches OB at D, and now draw a perpendicular, draw a tangent from through B to the given circle. Now you know that the radius OB would always be perpendicular to a tangent. This is basic school geometry. And now extend the line OC so that the tangent through B meets OC at the point A. Now I will calculate the angle of OBC, which is this angle OBC. Then I will calculate the sector O, circular sector OBC. So the circular sector has this additional area. this one. The circular sector has an additional area which is this one. So, the circular sector OBC is the triangle OBC plus this additional area and this red marked area, and then we will calculate the area of triangle OAB, and of course you can know that the triangle OAB includes both the circular sector and the triangle OBC. So, and that triangle OBC's area must be smaller than the area of the circular sector, and which is smaller than the area of triangle OAB. Now, once that is done, I need to calculate the area of triangle OBC. I am not going to do this simple school geometry for you. Area of a sector, people might worry, how do I find the area of a sector of a circle? So, if this is my S and this is my theta, how do I calculate the area of a sector? S is actually equal to half r square theta, right. For example, if I have taken a semicircle, then S would be nothing but half of pi r square if r is the radius. Here the radius is 1, so it will be, so it is half of the angle subtended at the center if the radius is 1. So, it is half of theta, which is half of x, half of theta if the radius equal to 1. And then also I am not going to find the triangle OBA for you, this is very basic geometry. When you listen to this talk, you can stop the talk and then you can try to calculate them and come back. So, now what does it mean? The area of triangle OBC is strictly less than the area of the circular sector OBC, and that is again strictly less than the area of triangle OBA. So, half of sin x is strictly less than half of x, which is strictly less than half of tan x. So, sin x is strictly less than x, which is strictly less than tan x. So, if x is not equal to 0 and x is very near 0, then sin x is not 0 and we divide by sin x. Of course, this division is assuming that I have taken x to be very small and sin x is of course not 0 in that case. So, once this division is done, I can then revert back to have cos x strictly less than sin x by x strictly less than 1. Now, all of us knows that cos of x is a continuous function at 0, because limit of cos x as x tends to 0 is 1, that you know. So, if you just look at the graph of cos x, you know what I mean. Now, how do I get the fact that the limit of sin x by x as x tends to 0 would also be 1? For this we introduce, or not introduce, rather we state here what is called the sandwich rule. The sandwich rule states that okay, if you have a function f lying between two functions h and g, and when x tends to a, if both h and g tends to the same limit L, then f will also tend to the same limit L when x is tending to a. So, here if I take limit of cos x as x tends to 0, that will go to 1, and limit of 1 when x tends to 0, because it is independent of x, will just go to 1, it will be just 1. So, since f is here, f is playing sin x by x is your fx, gx is just gx equal to 1 constant function, and hx is your cos x. Now, in our case, limit of cos x as x tends to 0 is 1 and limit of 1 as x tends to 0 is 1. So, we conclude that limit of sin x by x as x tends to 0 is 1. What way this limit is useful? For example, if I ask you to compute the limit of what will be the answer? It looks very surprising, again it is 0 by 0, but now we can write this as sin x into sin x. So, now we know that limit sin x by x is finite quantity, which is 1 as x tends to 0, and limit sin x as x tends to 0 is 0. So, you know that the multiplication rule, that if f and g are two functions and both of them tend to some limit, then their product the limit of the product is the product of the limits. So, these are all high school maths. So, I am not getting you putting too much stress on actually stating them, but you need to. So, now we will have that this is nothing but limit of f x tends to a into limit of g x tends to a. Now, sin x by x, so limit of sin x by x as x tends to 0 is 1 and limit of sin x as x tends to 0 is 0. So, this answer is 0. So, you can have a lot of problems of this form and it really does not matter. For example, if you have say limit of all these sort of trigonometric limits, limit of x tends to 0 sin x into cosine x by x. So, what would be the limit? Of course, I leave these things to you. So, what we have done is given you a very broad idea in these 3 lectures about very important concepts about limit and continuity. With this idea we will be able to move forward from the very basic working of with functions to the first steps in true calculus, where we are going to talk about derivative. So, it is very good to give a very brief introduction of what is going to come next. We are going to start talking about derivatives in the next lecture, but let me give you just a very brief idea of what's going. So, this idea of derivatives was first introduced by Leibniz and of course by the great Sir Isaac Newton, who brought it in to study mechanics. Derivative represented the velocity of a particle, instantaneous velocity of a particle in motion, maybe along a straight line, does not matter. So, there Newton wanted to look at the following, that if I look at the velocity of the 2 objects at 2 very close points, or rather I look at the change of displacement in a very short time. So, then this ratio is the velocity of the object within that very short span of time. So, when the time becomes very small, where does this ratio tend to? Earlier Greeks obviously thought that such things are impossible, motion is almost impossible, but that is really not true, and what Newton showed that yes, indeed that can tend to a non-zero quantity. And people thought, okay, whatever when the time becomes small, this distance will also club to 0, but they will actually get something meaningless, 0 by 0. So, this is not really true. So, then that idea of the rate of change of a distance, which we started calling velocity or instantaneous velocity, became one of the main sole fact in mechanics. Velocity and its second derivative, the acceleration, which actually led to Newton's second law, force is mass into acceleration, became the cornerstone of mechanics on which all of modern physics is built. So, it is very important to study derivatives, and we are going to study this thing. For a mathematician, it is important to know that derivative is defined in this following fashion. I am giving you this definition so that you come back with a little bit of refreshment of your refreshing your class 12 notes or class 12 things, your books, whatever you want to do. Now, this definition here, h of course means h is going to 0 from the right and h is going to 0 from the left. So, both ways, and this notion of a derivative of a function is also central to all mathematics. So, this is a very important notion that we are going to start studying in the next class. So, please understand, and I want to make it very clear that the famous mathematician who rather invented the amazing geometrical notion of fractals, Benoit Mandelbrot, had once said that you would understand calculus much better if you know at the very outset that every continuous function need not have a derivative. So, with this I would like to stop today's talk, and I hope that you go through this derivation, this geometrical derivation of the limit of sin x by x as x tends to 0. It is a good thing that lot of things can be done by Euclidean geometry. It also shows the geometric reasoning. Thank you very much.